We can also look at the idea of using conjugates as we're learning how to divide complex numbers. But before we get there, let's just back it up a little bit and let's look at this multiplication problem. Do you notice that 4 plus 7i? I'm multiplying it by its conjugate. So what do we get when we do this operation? Well, we can FOIL it out. So we have 4 times 4. So first times first. Outers gives me a minus 28i. The inners is a positive 28i. And the last term times last term gives me a negative 49i squared. And then cleaning that up a little bit, I notice that my inner terms cancel out. So I'm left with 16 take away of 49 times a negative 1, because I squared is negative 1. That results to 16 plus a 49, which equals a 65. So we can FOIL it out, or if you recognize an easier way if you want, you recognize that these are a difference of two squares, essentially. So first term squared, which let me rewrite it out. So 4 plus 7i times 4 minus 7i. If I recognize it as a difference of two squares, that's first term squared. Take away last term squared, which is a 49i squared. There, try to get the I squared in there. And you can see I'm back to where I was earlier. This becomes 16 minus a 49 times a negative 1, which equals 16 plus a 49 and equals a 65. So based on those two examples, we can recognize that if we ever have something in the form of a minus b I times a plus bi, that its result will be a squared plus b squared. And the reason why we have plus is noticing when we use the difference to two squares, there's an I squared that gets added onto the end. The I squared is a negative 1, and so a negative times a negative becomes a positive. So we recognize that this is true when we're dealing with conjugate pairs. We can just simply look at that model right there. So what do we do with this? How is this useful? Well, it's useful in a lot of different ways. One way it's useful is we can learn to divide. So let's look at 7 plus 4i divided by 2 minus 5i. To simplify it, we need to remove any imaginary parts from the denominator. So in order to do that, we're going to multiply by its conjugate and form that into a clever version of 1. So its conjugate is going to be 2 plus 5i. I'm going to use that as my conjugate pair to make my clever version of 1. Then from there, top times top, bottom times bottom. Which one do you want to do? Well, I'm going to work on the denominator while you work on the numerator. Denominator then, if I recognize this fashion right here, that's first term squared plus the 5 squared. Which, and I can work that out a little bit. The top looks like I'm going to have to do some FOIL here. So 7 times a 2 is a 14. Outers gives me a 35i. Inners is an 8i. And outers is a 20i squared. Collects and combine some like terms. So let's go ahead and collect. So we have a 14. The middle terms becomes a 43i. The last one is 20 times a negative I, or negative 1. So I'll make it a minus 20. The denominator, 2 squared plus 5 squared, with 4 plus 25 gives me a 29. And then from there, I can add the like terms. So I have 14 minus a 20 gives me a negative 6 plus a 43i all over a 29. Now, one last thing before we finish this problem, I want to see that you notice that when I multiply complex pairs, where one's the conjugate of the other, well, what's my result? My result's just a real number. It's not a complex number. Well, it doesn't have any imaginary parts. Let's say it that way. So that's kind of a cool idea that I can multiply two complex numbers and the results are just the real parts of those numbers.